Так, ребята, но мы давайте начнем тогда потихонечку, потому что люди заглядывают.
Let us start because people start peeking into our room, nothing is happening here, and then they choose the coffee and the buns. So let us listen to Marcus Нуллмайер. He's going to tell us about accelerating queries of set data types with GIN, JSON, and custom indexing accelerators.
So hello everybody, I'm Marcus Нуллмайер from the University of Heidelberg. I work in a small group working on public astronomical databases. And today I'm going to speak about our special topics for indexing, mainly for so-called set data types. And for Postgres, obviously. So does this here work? Wait. Here. No, it's not. No. Anyway, sets do come up occasionally when we want to model data. That is more complex than just integers or strings or something. I mean, I think you have the best idea with your own domain knowledge where they may occur. There is no data type called set in Postgres, but you could use various that are already there. For example, the hash-like data types such as JSON-B and HStore. I mean, JSON is of course much more complex, but you could just use one hash in JSON and use a set for that. Another option is to use sorted arrays, which are also provided in stock Postgres. All right. Postgres, when you install it, already has quite a few useful operations for data types that can be used as sets. Here I use integer arrays from the extension int array from the contrib part of Postgres. This is probably the most comprehensive as regards operations set data type that you have in Postgres. Anyway, as this is a talk about indexing, we want to accelerate some of these queries that we just saw in the slide before with indexes. And one very popular technique to do this is a so-called, generally called inverted file technique. This is the terminology of the set guys, or it's more commonly known as an inverted index. So those of you who have been to the RAM talk already know all the details, how it is implemented internally in Postgres, in the RAM, or in the very similar GIN index that comes with stock Postgres. So it just works like this. This is just a short catch up. So the set elements are used as keys, and the whole sets are the data types of the column that you index. And so this inverted file, inverted index technique is good for so-called point queries where you want to find a single set element. And it's also quite widely available in Postgres, as we see, for these int array, JSON-B, HStore data types. And also for other queries, such as superset queries, you have only with the int array data type in Postgres also the option to use the so-called RD trees. So there's a special kind of R tree. I mean, we just heard 2 hours ago the talk of Andrei Borodin about his improvement in GIST, and these RD trees are also some D trays that are optimized for sets. Okay, and if you have queries like these, you can use it in Postgres. So this was so to speak, a small warm-up, and sort of the main intention was to give pointers to those of you who are interested in that many things are already available if you would need them. And that they are quite usable as long as the sets don't get too big. So if it's in the order of tens of megabytes for one data type, I mean, this is possible in Postgres, then you probably get performance problems. But the index support is there. However, when you want to operate on a single datum, so a single exemplar of a data type in Postgres, for most of them, they have to be loaded in memory from disk to memory to do any operations on them. There are some exceptions, for example, substring operations. You can do, then only the substring is read from the disk. And as far as I know, there are some activities to remedy the situation in JSON-B, if I remember correctly. Okay, so however, if you have a domain-specific requirements for your sets, then it could be that these built-in functions of Postgres set capable data types are not enough. And for the remainder of the talk, I will talk about the use case in the field I'm working in astronomical databases. So let's take a look here. What we see here are 2 examples of coverage of the sky. So these are spheres of astronomical surveys with whatever kind of instruments. I don't know what kind of instruments they use. Oops. So it's often that just here parts of the sky are covered, and when then scientists want to evaluate these data for their research, they of course want to know which surveys are at certain positions for or in a certain area in the sky, for example, if they want to put sources together from measurements together from various sources. And so just the information in one of these 2 or many others, there's a public database of these with almost 20,000 of sky coverage data for various surveys. So each one of these 2s and these other 20,000s is one set, and it's a very complex structure. There are here small patches in there where there's no coverage, and then there are sometimes big areas where there is something. And so what we basically can't do is it's inefficient to have a discretization where all these small areas are resolved everywhere. And what you here can already see, there's some multi-resolution technique going on, as we will see in the next slide. Oops, yes. So I will go in the inverse order. So what is done there, as you can see here, it's a bit small maybe, that you just need 2 values, not shown here, for each of these elements. So this is a begin and start and values, something like a space filling curves if you want to. And what here, this slide just gives more information about the specific background. If you have some background here, so the data type that I am involved in is a so-called multi-order coverage of a specific kind, and this spatial discretization is called HEPIX, but this is not really important. What is important is that many of these public astronomical databases actually use Postgres. Some use something else, but Postgres is basically very strong there. And now I'm coming to the details of the implementation. So conceptually it's very easy. All these sky maps are represented by a very long, maybe sorted array, if you will, of half-open intervals. The difference is here that we have intervals and not single points in the set. I mean, having single points would be way too big for the data. And so here are some details that basically the numbers here are just the some linearization, linear coordinate in the smallest resolution, and if we've got a big patch, like a big square, then we still have just two numbers. Okay, so what we need is to have this guy as a data type in Postgres. And what typical queries are there are point queries where we have got a point on the sky and want to return all the multi-order coverage, these sky maps, where this point is covered, or a bigger area on the sky. Okay, so this is what I implemented. And here are some further details. So if you want to know if just one point in all these intervals, for example, 350 is covered, well, for this small size it's okay, but if you've got millions and millions of intervals, then it takes some time to get this all through the Postgres disk buffer subsystem. And I solved it in, I guess, sort of obvious way to have some structure to make this fast. And if access to data is slow, but the data blocks can be sorted, the method of choice is, of course, a B tree. And so what I did is implement a B tree for each single datum. I should have made a sketch here. This is unfortunately missing. But I hope you know what a B tree is, and if not, look it up. It's a really nifty data structure, which is of course used in the main indexing for Postgres anyway, with much more features. Anyway, so Postgres is like this, that if you have a data type, then it's never modified, the contents. If you modify a value in a table, it's overwritten by something new, and all the old stuff is, well, eventually forgotten, let's say. And so this makes the access actually easier, because first, when I build this datum from input, I have a sorted list, and from this sorted list, I build a B tree, and the features there are that it's basically more or less fully filled, so there's no space wasted. And it's also perfectly sorted, so the linear access is also possible, because it's just stored there like this on disk. And for those of you who are a bit already into the internals of Postgres, the technique to store large data in Postgres is called toast, and the pages of the B trees are mapped to the slices of the toast subsystem to make this a bit more efficient. Okay. However, even if you have got only like 3 or 4 page accesses to get to one point on one of these sky maps, still, if you want to query all of them, you have to get to all of them. You have to do a sequential scan. So the question would be, is it possible to use similar techniques to these inverted index that is used for sets where all elements are explicitly represented, like in the beginning of my talk? Is it possible to make this work with this run length encoding technique? I mean, it's clear that if you've got millions of values between, well, here you've got just thousands, but in reality you have millions and billions. You can't just put all the elements in. I mean, then you could use these GIN indexes, for example, in Postgres, but, well, here it's not feasible. However, if one would do a slight modification to this, namely not use the single elements of the set as keys, but the intervals, then it should work. Then you have something like, if you have been to the RAM talk, something like the RAM or GIN structure. Here you have basically the sorted version of the entry tree, and here you have these posting lists or posting trees. And then you can quickly go to, let's say, search for 0.6000, and you go here, and then you get all the sky maps that are that contain this point. So that would be good if we would have something like this in Postgres. And this is the main talk. So the main topic of my talk. However, it's important that these intervals must not overlap, because otherwise we would have no real improvement from the index. And this, as I said before, GIN is not possible. However, with the newly last year released RAM access method for Postgres, there was, I saw a way to solve this problem. There are many points that are important here. First, is that it is usable as an extension to Postgres, because the most astronomical data centers can't afford to maintain a patch to the core of Postgres. However, an extension, this is quite feasible, and actually they use other extensions to do other stuff for astronomical queries in database. So this is, an extension is possible. And so this is something. And also RAM is basically the heritage of GIN, so there is the infrastructure already there of an inverted index. And then, of course, it's important that it has a Postgres license, because we as public astronomical data centers, we don't have a budget for expensive software. However, I had to make several modifications to make this work, and now I introduce this USO project. So why it's called USO, so the official inverted meaning will be announced later, but it's unimportant, just it needs a name. So what is it? It's basically an involvement of the RAM code, just an extension. I mean, and it's also important for me to make this feasible, because I can only work part-time on that, that all this difficult part of indexing in a multi-base back-end database system with all these concurrencies, they are already solved in RAM. So I don't need to work on that. This means that all these internal B-tree code that the indexing that is at the core of the indexing in RAM can be reused, both for the entry tree where the intervals are stored and also for these posting trees. And it's also possible to make this backward compatible, meaning that these modifications don't alter the behavior of RAM. It's just additional features that I'm working on there. And what it does is that you basically can index any kind of sets that are comprised of intervals of whatever type. So it is generic in a similar way that RAM already is for other data types. And unfortunately, I don't have it ready yet. I really would have wanted to present benchmarks, but this is for another time. So what did I need to do to make this work? There are three main fields that needed to be done. First is that the intervals basically in the entry tree are different from what is in the single indexed sky maps. So this means that if you add a sky map to a column that is indexed by these indexing method, it's just not an insertion of one thing, of one element, but some of the intervals will have to be modified and others will have to be added. So I will explain this in detail on the next slide. And the other point is that when you search for insertion and also later for queries from the index, the search in the index must be relative. So I will explain this later as well. And also I had to add some so-called support functions for the so-called operator class, which, if you don't know it, I'll explain later. Okay. So here I've got a very simple explanation. What I mean, it's hopefully not too trivial, but for example, let's assume that we see here one part of the entry tree of the index before the insertion of this interval. So this object may have other intervals, but all of them, of course, have to be added to the entry tree. This is normal for an inverted index. So let's see that the index in this area looks before like this. And afterwards, so it goes from 32 to 128. And from 96 to 128, we have also the object 108 that has elements there, and this means that the correct index after the insertion looks like this. So this first interval has to be modified, which is normally not done, of course, in inverted indexes, but if they are sorted, this is possible. And the second interval has to be A, inserted, and also because the interval before covers this space, the objects from there must be copied. And this is, of course, because one interval boundaries match is a sort of simple case, and surprisingly, if one looks into it, there are 13 possible cases that one has to consider. More information on that on the next slide. Hello? Sorry. Here. So there are some issues with this interval insertion. If you would do it the naive way, you would have to basically lock insertion into the index for a long time. Imagine that for some reason there is one interval that covers a large area of the sky, and this means that many of these and other objects basically are very fragmented there. So that would mean you have maybe to change thousands, millions or more of intervals, and this would be very bad for concurrency if this would mean that the index is locked for the whole time. Luckily, this is not necessary. We can do this bit by bit, and at most have to change 3 intervals at the time, where other processes can't modify the entry trees. So this is relatively okay. Still, when one of these 13 elementary modifications like these have to be done, at least the index at least has to be locked for writing. For reading, it should be okay. 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 The only problem is I basically didn't test it yet, so could be that I overlooked something. So now we have covered the first point that had to be modified from room to get to the SkyMac indexing, which is interval insertion. The next main point is the searching inside of one of these B trees. To get these interval insertion and also later the queries with intervals work correctly, one has to have results not only from exact matches, but also from sort of the nearest interval to this point in the direction. And this is a so-called lower bound search. Lower bound here means that the thing you are searching for is the lower bound for the results. So the result is either equal to the search term or the value is higher. And RAM doesn't completely provide it like now, right now. So because these normal inverted indexes just search for as far as I know, for exact matches. Well, I mean, the implementation that is almost like this, but in some corner cases not, and so this had to be modified. However, this is not too hard to implement because internally RAM is relatively cleanly structured, and so for these operations on B trees, there's basically something like a C-like class with quite a few virtual methods, and only 2 of them have to be modified, namely to find something in a tree page, or the other one to find something in a leaf page. Right. Okay, now I come to the last point. If I'm going to release it, I'm going to release it with the same license as RAM itself, then maybe somebody would like to add indexing with their own custom data type. And this is actually not too hard to implement yourself. So for GIN and GIST and these indexes, it's done with so-called support functions. They have presumably an SQL interface, but I put it in inverted commas because in reality these are C functions that only are called with SQL wrappers. And for the case of Uso, it's not much that has to be done. Basically, one has to provide 4 functions. Well, one thing before, I don't have a slide for that. So we have 2 data types here, one interval and internal. Of course, the interval data type you have to implement yourself, but this is out of the scope of this talk, but it's also relatively straightforward, and there are even tutorials on the internet for that. And so we need to have the data type, obviously, and then we have to have these 4 support functions, these C functions disguised as SQL functions. And it's very simple. You just need to get some internal representation, basically a pointer that only you as the implementer know what to do with it. So a pointer to a left boundary of an interval, a pointer to the right boundary of the interval, a function to compare boundaries of the interval. This is of course needed to make the sort order of the intervals internally work in the B-tree indexes. And also, obviously, a function to create a new interval data type when the boundaries are given. And everything else, including partially also the sort operations, should be provided. So this is my last slide. In conclusion, I would say that it was basically easier than I would have thought in the beginning. So, and if anybody of you has a need to in custom indexing things that are somehow similar to the things that RAM offers, don't hesitate to contemplate to make modifications yourself, because on this, at least on this high level that I only had to use, it is relatively straightforward. So, yeah, that's it. So, thanks for your attention. Any questions?
Спасибо, Маркус. Вопросы? Такой хардкорчик нормальный. Ну, давайте.
Thank you. If it is an index, can we use it for example, date intervals, or it's
date? Yes, certainly so.
So I shouldn't transform them to Unix time. Just I can use them for date 1, date 2.
Yes, I mean, well, I haven't implemented date, but one could use even. I mean, Postgres even offers some interval-like data types, and they could be used for that. I mean, I'm personally not into date. Into date data types, so I don't know if there's a date interval data type in Postgres or just a single. But it's certainly possible without really problems. So and it should be fast once Uso is ready to implement, because these support functions that I had here on the last slide, they are almost trivial. I mean, as long as you don't dare to use C, you can do it quickly.
Thank you.
Thank you very much for your lecture. My question is, how many elements in a set have you faced in your work? So there were millions.
Yes,
hundreds,
millions.
And what's about the speed of index?
Well, I didn't have made yet, unfortunately, a systematic benchmark, so it's all relatively new.
But when you were using B-trees with points, just points, not intervals in them, what was...
Well, actually, what's the word? I basically skipped that point, I never implemented it with points. I directly went for the interval data type, and others do this as well for these sky maps. So there was no questions, just to go straight to intervals.
So it is just a development testing, but not you haven't tested it with real data and with real millions of stars.
Well, not systematically. I will do it later this year for the astronomy community, for the astronomy database community, but not yet. It's bit new. Anyway.
Thank you very much.
Yeah.
Okay, thank you. And don't you think about using geographical extensions for mapping sky map? As I saw in first slides, you have angular coordinates of observed maps.
Mm-hmm.
So why don't you use observed polygons like in geospatial systems? They have already a lot of speedups and techniques.
Yeah, well, there's I mean, what we use are also polygons, and some in the astronomical database community, for example, use PostGIS or other geospatial, mainly PostGIS for that. However, for astronomy, there is a sort of PostGIS-like extension for Postgres that is more suitable for astronomy, and it also has polygons. However, the problem, I will go back to answer this question to the slide with the sky maps here. So the point how the way it is done that these polygons are indexed to make searches fast there is at least for PostGIS and this PGSphere, the astronomy equivalent for PostGIS, is done with also with these so-called R trees, and it works internally like this, that a 3D bounding box, as was explained in the GIS talk later today, is put around the polygon, and meaning that once you're in the search process, you found the indexing machinery. Once the indexing machinery has found this bounding box, all what's inside the bounding box basically must be verified. So, and as you can see here now, if we have things like where the whole sky is covered, basically the indexing degrades to sequential scan, because you have to look, the bounding box of something like this would basically cover the whole sphere. So it won't be any faster. So the point here is this is a very special case. I mean, what is also used in astronomy that you have smaller areas of interest, and there people are using it. I mean, my boss is using it on his data center, polygons, but they must be relatively small for the indexing to have any effect. This classical R tree indexing. So, yeah.
Okay, thank you.
And so you haven't used GIST because GIST doesn't return the true value, and you have to make sequence scan just to prove.
Sorry, could you repeat more slowly?
Yes, sorry very much. You didn't use GIST because every result returned by GIST index should be rechecked from the table. And do I understand right that you avoid sequence scan in any time and you are just using only RAM index, but you never go to just a heap table?
Well, of course, if one wants to do more specific checking, such as subsets or something, I just right now have only implemented point scan, but with other types of scans, such as some kind of subset scans, you will also have to go to the heap table. It depends on the operation that that the index is accelerating.
And can I ask you how big is the heap table in astronomy?
Well, I mean, I'm worked mainly on this database backend things, but they can be of the order of terabytes. I mean, for example, sorry?
One table.
Yes. I mean, I mean, they can be small, but they also can be very big. For example, last September there was the release of the first preliminary, but still first release of the measurements of the Gaia satellite, and this satellite measures distances and also velocities of stars in quite a big part of the Milky Way. And this first release has like almost 2 billion objects there, and with all additional data there are like maybe order of 100 columns there, we have the order of 1 terabyte.
And have you thought about sharding or partitioning within this table?
Well, I personally know. I mean, some people are interested in that. This I know, but I don't know if every. Yeah, I mean, some people are doing it in some ways, but I'm not an expert on that. I'm sorry. So it's relatively uncommon, but it will be used more in the future.
Because yesterday there was a very interesting lecture about sharding, where you should make only a scan only of a shard, only of a partition.
Yes.
Yes, and maybe it would help you. And you
it could.
So much.
Yeah. I mean, probably not for these sky maps, but for the regular things where there are only star positions and colors and these things. Certainly, yes. I also agree that this is most likely the future there. Thanks.
Any question? Давайте поблагодарим, ребята. Thank you. Dankeschön.